Okay, objective 7 for Unit 4 in Honors Math 3, graphing rational functions with slant asymptotes. Now that's the new part. That's not to say that every problem that we do will necessarily have slant asymptotes. But the new part here. So slant asymptote, by the way, slant could also be named oblique. So an oblique asymptote is the same thing as a slant asymptote. A slant asymptote will exist only if the degree for the numerator is exactly 1 degree higher than the degree for the denominator, and the degree for the denominator must be greater than or equal to 1, even after reducing. So remember what I talked about. If there are no x's left in the denominator, there are no asymptotes, period. So you got to have at least one x still in the denominator for there to be any asymptotes. If this is all true, then we find the slant asymptote, SA for short, by division. And you do not need to worry about the remainder. Okay, let's do some sample problems here. So let's say we have f of x equals x squared plus x minus 12 all over x plus 2. Now, if things factor, it's good to see factored form, because if it reduces, we need to see if it reduces. There's a hole in the graph if it reduces. So, for example, the x squared plus x minus 12, that factors as x plus 4 times x minus 3, and the denominator is x plus 2. Does it reduce? No, it does not reduce. So, vertical asymptotes, we have a 0 in the denominator, a real 0 in the denominator, so x equals negative 2. Does the limit exist as x goes to infinity? No, it's top-heavy. So the horizontal asymptote, there is none. The slant asymptote, is this a situation for slant? Well, the degree in the numerator is exactly 1 higher than the degree in the denominator, and we do have x's in the denominator, so yes, there will be a slant asymptote for this particular problem. How do we find it? We find it by division. Now, I did not specify what type of division. If you can do synthetic, I would suggest do synthetic. If you have to do long division, then do long division. Okay, now, we're dividing by x plus 2. That's x plus 2 to the first. So I can do synthetic. So negative 2 in the box, 1, 1, negative 12. It's all set up. Okay, and so 1, negative 2, negative 1, 2, negative 10. But what did I say about the remainder? I said you don't have to worry about it at all. Okay, this is remainder, so we're not worried about the remainder. Okay, so where is the slant asymptote? Well, let's remind ourselves what this is. We started with x squared plus x minus 12. I divided by x plus 2, so this would go from a second degree to a first degree. This would be x minus 1. Now, it is a slant asymptote, a slant line. So, well, vertical lines are x equals, but isn't every other type of line y equals? Yes. So the slant asymptote is y equals x minus 1. So there are the asymptotes for this particular problem. Okay, let's try another one. Number 2. So number 2, we've got y equals 2x squared plus x minus 6 all over x plus 2. Okay, so again, I think it's a good idea to go ahead and double check. Make sure whether or not the function reduces or not. So the 2x squared plus x minus 6, Looks like we might be able to factor it. We can't always factor these, at least not over the integers. It only reduces if you have a factor of x plus 2. So I'm going to use that and see if that works. So 2x and 1x, and I would need the 2 away from the 2x anyway. So let's see, that means this would be a 3. Let me see. So how about x plus 2 and 2x minus 3? Does that work? Yes, that works. So it's factored. Does this reduce? Yes, it does reduce. And so we have a whole at x equals -2. Specifically -2, comma. And if I plug in the -2 into the reduced equation, we have -4 minus 3, -2, comma, -7. There's a whole at -2, -7. Now, do we have any x's left in the denominator once I'm reduced? No. So what does that tell me about asymptotes? There are none. There are no vertical, there are no horizontal, and there are no slant asymptotes. It's just the equation of a line, y equals 2x minus 3, with a hole at the point -2, comma, -7. Okay, now, that's just finding the asymptotes. Let's actually follow through and do the graph of one of these. Okay, so let's say that we've got, we're gonna go ahead and do the sketch here. Sketch, label the intercepts, and graph the asymptotes. Okay, so problem number 3, g of x equals x squared minus 5x plus 4 all over x minus 2. Okay, so we can see there's a real 0 in the denominator of 2. And let's factor the numerator. I think it's x minus 4 times x minus 1. So yes, it does not reduce. So vertical asymptote, x equals 2. Horizontal asymptote, does the limit exist as x goes to infinity? No, it's top heavy. So there is no horizontal asymptote. Is this a situation for slant? Is it top heavy by 1 degree? And are there x's in the denominator? Yes. So there is a slant asymptote here. We just have to find it. How do we find it? By division. So, and I'm dividing by x minus 2 to the first. So yes, we can go ahead and do synthetic division. So 2 in the box, 1, -5, 4. Okay, and the remainder, remember, you don't have to worry about the remainder. And this is x minus 3. And so our slant asymptote is y equals x minus 3. Okay, so when we go to graph this now, when you have a slant asymptote, a lot of times we end up having to do the vertical asymptote up higher or down lower. So x equals 2. Y equals x minus 3. Now, strong suggestion here. When you graph the slant asymptote, obviously you could do y-intercept and the slope. So the y-intercept is -3. And the slope is +1, so up 1 over 1. However, I strongly recommend that you not just graph it like that. Get the x-intercept for the slant asymptote. So if I plug in 0 for the y, wouldn't x equal 3? Now, why do I recommend that so much? because I've seen students not be real accurate with where it's crossing the x-intercept or where it's crossing the x-axis. And because of that, then when we do the x-intercepts for the function, then you might have it on the wrong side of the slant asymptote. So, strongly recommend that you graph the slant asymptotes by their x and y intercepts. Okay, so here's my vertical asymptote, there's my slant asymptote. Now, slant asymptote, as far as the graph goes, it behaves similar to the horizontal asymptote. As the graph goes to the left and the right forever, the graph will go toward the slant asymptote. So as it goes to the right, it's going to go toward the slant asymptote. As it goes to the left, it's going to go towards the slant asymptote. Still, the graph never ever touches or crosses the vertical asymptote, and there's always one more piece of graph than there is vertical asymptote. So, two pieces of graph, one on the left side and one on the right side. Okay. Now, x-intercepts, y-intercepts, yes, let's do that. So, x-intercepts works exactly the same way as when we were doing the horizontal asymptotes. So if I plug in 0 for the y, focus in on the numerator, 4 and 1. And again, the multiplicity, if it bounces or crosses appropriately, all that kind of stuff. So 4, 0. Now 4, 0 is on the right-hand side of the slant asymptote there. And 1, 0 is on the left-hand side of the vertical asymptote. Okay. Now, how about the y-intercept? Well, the y-intercept, if I plug in 0 for all the x's, we get 4 over -2, so 0, -2. Okay, so I've got my y-intercept here, I've got the x-intercept there, the multiplicity is 1, it goes through, it doesn't touch or cross the vertical asymptote, so it looks to me like I'm starting up high, I'm going through, and as I go to the left, I go toward the slant asymptote. Label. Okay. Now, over here on the right-hand side, again, the multiplicity is 1, so I have to go through. As it goes to the right, it goes to the slant asymptote. So I have to be crossing and going towards the slant asymptote. So doesn't that indicate I'd need to be coming from down low, close to the vertical asymptote? Wouldn't make sense to be coming from up high because I'd have to cross the x-axis there somewhere and then go through. So that's not where. So I must be starting from down low, going through that x-intercept, and then it continues on towards the slant asymptote as I go to the right. Okay, so there's that graph. Let's try another one here. So number 4. Okay, so number 4, let's say we have h of x is equal to x cubed minus 1 all over x squared minus x minus 6. Okay. If I factor it quickly to check and see if things reduce, the denominator is x minus 3 times x plus 2. And the numerator, that's difference of cubes, so x minus 1, x squared plus 1x plus 1. And promised you back at quite a while ago that if you do sum or difference of cubes, that right-hand side does not factor over the reals. There's 2 roots in there, but they're imaginaries. And so they're not going to reduce with anything down here, and they're not x-intercepts either. Okay, so nothing reduces. I have 2 zeros in the denominator, so vertical asymptotes, x equals 3, x equals -2. Horizontal asymptote, none, because it's top-heavy, so the limit does not exist as x goes to infinity. Slant asymptote, it is top-heavy by 1, and there are x's in the denominator. Can I do synthetic division? No, I'm dividing by x squared. So we need long division. So x squared minus x minus 6 into x cubed minus 1. I'm just going to spread that out just a little bit right there. You don't have to do placeholders. You can just spread it out a little bit. Okay, what times x squared gives me x cubed? Well, x. So x times x squared is x cubed. X times negative x is negative x squared. And x times negative 6 is negative 6x. Nice to have an alternate color so you can see that you're distributing the negative. Negative. This becomes positive. That becomes positive. And so we've got x squared plus 6x, and bring down the -1. What times x squared gives me x squared? Well, plus 1. So I get x squared minus x minus 6. And if I distribute the negative, and we've got 7x plus 5. Okay, now does x squared go into 7x plus 5? No. So what is 7x plus 5? It's remainder. You can essentially disregard the remainder. Now I'm not obliterating it. I do want to point something out to you in a little bit. Now, what is the slant asymptote? Well, it's y equals x plus 1. So the answer to the division problem, and we get to throw away the remainder. Okay, so graphing this, vertical asymptotes, x equals 3. X equals -2. And y equals x plus 1. So y-intercept is 1. And if I do the x-intercept, like what I was talking to you guys about, if I plug in 0 for the y, I get x equals -1. Okay, maybe even do another point there, up 1 over 1. Okay, so slant asymptote. I think I already mentioned to you that when you have a slant asymptote, a lot of times you need to make the vertical asymptotes go up and down a little bit more than normal. Okay, 2 vertical asymptotes, there will be 3 pieces of graph. Something out here to the left, something in the middle, and something out here to the right. Okay, the x-intercepts, if I make y equals 0, I have an x-intercept at 1. So x-intercept 1, 0. Its multiplicity is 1. It does go through. There are 2 roots in here, but they are both imaginary. So 1, 0, and it goes through. Y-intercept. Y-intercept, if I plug in 0 for the x's, we get -1 over -6, which is positive 1/6. So 0, 1/6. Okay, this x-intercept goes through. It does not bounce. I have a y-intercept above the x-axis. This graph here in the middle must be coming from up high on the left and going through those 2 points and going down low on the right. Okay, label those. This one is 1/6, and that one is 1 right there. Okay, that's the middle section of the graph. Okay, now, we need to find out what's happening out here to the left and to the right. Okay, now, haven't we found all the x-intercepts? Yes, we have found all the x-intercepts. So, could I be starting close to the vertical on the left-hand side here. Could I be starting up high and going towards the slant asymptote as I go to the left? No, I'd have an x-intercept, and there are no more x-intercepts. Therefore, I must be starting from down low and then going towards the slant asymptote as I go to the left. So it's doing something like this. Now, in similar reasoning, here on the right-hand side, could I start from down low next to the vertical asymptote and go toward the slant as I go to the right? No, because there are no more x-intercepts. I only have the one. Therefore, I must be starting from up high and going to the slant asymptote as I go to the right, like that. And there's my graph. Okay, I would like to do one last problem with you here. Now, all the problems I've been working with in this notes are dealing with the slant asymptotes. That's not to say that every problem on the assignment will be a slant asymptote type of problem. But I've already done those notes, so I'm focusing on the new stuff. Okay, so let's say we have this function, y equals x to the third minus 3x squared plus 4 all over x squared minus 2x plus 1. Now, just to save a little bit of time, I factored things, and so the numerator factors as x plus 1 times x minus 2 times x minus 2, or in other words, x minus 2 quantity squared. The denominator factors as x minus 1 times x minus 1, or x minus 1 quantity squared. Nothing reduces, so we do have a vertical asymptote at x equals 1. This is not a situation for a horizontal asymptote. It's top-heavy, so there is no horizontal asymptote. This is a situation for a slant asymptote. And again, we cannot do it by synthetic division because we're dividing by x to the second. So we need to do that by long division. So x squared minus 2x plus 1 into x to the third minus 3x squared plus 4. Okay, so what times x squared? Well, x. So I get x to the third minus 2x squared plus x. And a different color so I can see the fact that I distributed the negative. And we get negative x squared minus x plus 4. So what times x squared? Well, negative 1. So I get negative x squared plus 2x minus 1. Okay, and if I distribute my negative, then we're left with negative 3x plus 5. Okay, now that is remainder. We don't need to worry about the remainder. I think I forgot to talk about that on the last one. I do need to talk about it on this one. So the slant asymptote is y equals x minus 1. Okay, so there are the asymptotes. Now, by the way, when the test comes around next week, there will be some problems. All we ask you for are the asymptotes. And so this would be an example of there's a whole page of problems like this. They just ask you what are the asymptotes. So vertical asymptote, horizontal asymptote, and slant asymptote. And if there aren't any for that one, you need to write none or something along those lines so that we understand that you know that there aren't any of that type of asymptote for that particular problem. Don't just leave it blank. Okay, so sketching the graph here. X equals 1. Y equals x minus 1. So y-intercept of negative 1, up 1 over 1. So there's the x-intercept as well. Okay, if we look for x-intercepts, we have x-intercepts at -1 and +2. And the -1 goes through because the multiplicity is odd. +2 bounces because its multiplicity is even. Okay, so let's get the y-intercept as well. The y-intercept, if I plug in 0 for all the x's, we're left with 4 over 1. So 0, 4. Okay, so based on all these points, we can go ahead and sketch it. So on the left side of the vertical asymptote, the -1, 0 had odd multiplicity. It goes through, so it goes toward the slant asymptote as I go to the left, and it goes through the y-intercept and gets closer and closer to the vertical asymptote. So it must be doing something like this here on the left-hand side of the vertical asymptote. Label the intercepts. Okay, now this one's a little bit trickier than any of the other ones I've given you, but what did I say about this x-intercept? It had even multiplicity. It bounces. So could it bounce and be going down? Well, that would be okay going toward the vertical asymptote, but the problem is, as you go to the right, the graph has to be going toward the slant asymptote. So it could not be bouncing down. Therefore, it must be bouncing up. Okay, now as it goes to the right, it goes toward the slant asymptote. And so it's really just going toward the slant asymptote from the bottom side of the slant asymptote there. Now, remember I talked to you about the fact that the graph doesn't just stop as it goes towards the vertical asymptote. So it bounced, it's going towards the vertical asymptote, it does not stop. It is possible for it to cross a slant asymptote, and it does on this one. And the graph is going up as it goes towards the vertical asymptote right there. Okay, now label the x-intercept there, that's 2. That would be a full credit graph. Now, let's talk about this a little bit more. I mentioned something about looking at the remainder. So, if you look at the remainder, if the remainder has x's in it, if you set the remainder equal to 0, so -3x plus 5 equals 0, we can actually find where the graph will cross the slant asymptote by setting the remainder equal to 0. Now, it doesn't cross the slant asymptote if there are no x's in it. But if I solve this, I get 5 equals 3x, and so divide by 3, and x is 5/3. Now, does that make sense with what we're seeing on the graph? 5/3 is 1 2/3. 1 2/3 is just a little bit to the left of 2, and that looks appropriate because it looks like we're crossing the slant asymptote at x equals 5/3. Okay, and so that's one way we can check what's going on here. Now, another thing that's happening too, most of the graphs, if you look at most of these rational function graphs, when we're coming up on vertical asymptotes, there's usually, you've got on one side of the vertical asymptote it's going up, and on the other side of the vertical asymptote it's going down, and that's typically what happens. That's probably the most common thing that happens. So one side it's going up, and the other side of that same vertical asymptote it's going down. One side it's going down, and the other side of that same vertical asymptote it's going up. So that's a typical thing that happens. Now, this one doesn't do that typical thing. Why is it not doing the typical thing? On one side of the vertical asymptote it's going up, on the other side of the same vertical asymptote, it's also going up. So why is it doing that? Okay, now let's take a look at the vertical asymptote. See how it's x minus 1 quantity squared? It's kind of like an even multiplicity for that vertical asymptote. Anytime you have an even multiplicity for a vertical asymptote, you're going to get them going both in the same direction, either both going up on either side of the vertical asymptote or both going down on either side of the vertical asymptote. Now don't focus on that part, but that is just kind of a handy thing to keep in mind. Much like if the remainder on the slant asymptote has x's in it, you can check to see where it's crossing the slant asymptote. It's not a critical thing, but it's just kind of a handy thing to be able to check.